Yep, thank you for that, Brent. And hi, everyone, again. We're going to talk about pumps, oftentimes taken for granted, but one of the key elements and the essential elements in the mill circuit. Just as the milling circuit is considered the heart of the whole process, the pump within the mill circuit process is the heart within the mill circuit process. Briefly, what we're going to touch on today is the different aspects, the role of the pump within the mill circuit, the operational challenges that the pump's going to face within that role, and the characteristics and features in which that will help the pump address the challenges. And very importantly, managing and maintenance the pump within the mill circuit. Okay, just briefly, that's your mill circuit diagram. You see the pump there. Essentially, when people talk about the mill circuit, the main focus is on tonnage per hour. Now, tonnage per hour has connotations of something dry, right? Whereas the pump, very differently, is always considered to be pumping a mixture of solid and liquid, and therefore we consider the measure of whatever we're doing with the pump in cubic meters an hour, the slurry flow rate. And what's going to affect the flow rate compared to your normal water pumps is your percentage of concentration. You'll have solids in there which come from the mill. Importantly, your particle size distribution. It could be fine, it could be coarse, and the density of slurry, that is how much ore is mixed with the water. Another important factor when selecting your pump, as you'll see the pump here, it's got to pump up to your cyclone normally, typically. And within that, you'll have a static head that the slurry has got to rise to, and also a certain length of pipe through which the slurry has got to be delivered. And at the end of all that, you're going to have a cyclone pressure, which the pump has to deliver to the cyclone so the cyclone can operate effectively. Right, now we're going to look at the challenges that the pump actually has in its operation within the mill circuit. The first priority that everybody considers the pump to have is high availability. It's got to keep on going all the time in order to keep the mill circuit operational. The other very important feature is it's got to deliver a constant feed to the cyclone so that the cyclone can do its classification act effectively. And at the same time, it's got to deliver the required pressure that the cyclone needs to have maintain its cut point, etc. It's got to maintain all this in the face of having to deliver media that is at the very outset of the mill circuit or any mineral processing environment. And the material is typically going to be coarse, it's going to be abrasive, and in most cases where people are reluctant to use too much water, you're going to have a high concentration of solids. Now, all these factors combined gives the pump a nice problem of high wear to contend with. And over and above this, you might have an upset condition where you might have to contend, or the pump has to contend with scats or oversized or tramp material which might come through after the mill. So let's just have a look at the criterion, the different criteria and the characteristics of the pump that will address these requirements. Firstly, you're going to have a constant feed to the cyclone, and it's got to have a certain pressure maintained to the cyclone. That's what the pump's got to do. What's very important here is, remember, the pump is not a process piece of equipment. It's something that's transferring your slurry. It's not doing anything to the slurry other than transferring. So it's not crushing or grinding or classifying. So the important thing to remember is it needs a constant supply, and by constant supply we need a tank or a hopper that's got a constant supply within it. And an important factor there is to have some sort of level control in the feed sump. So you maintain a constant feed into the pump, and then the pump can take the process further. One other important factor is the use of VSDs with the pump, variable speed drives. This is to counter any variation you might encounter in the feed or if your density changes, etc. But there's also a different aspect where you might find wear on the pump itself, and the VSD is also effective in helping with that. The other important factor in maintaining availability of the pump and making sure that the pump is delivering a consistent flow into the cyclone is to have some sort of adjustment facility. This is primarily because of the nature of what the pump is handling, you're going to get wear within the pump. So your impellers and your liners, I think Waldo described the different modes of wear, impact, abrasion, etc. All these come into play within the pump. And with an adjustment facility to ensure that your liners and impeller adjusted optimally to deliver, to maintain that flow, it will also counter any wear effects. Taking a further look at the criteria, and that's your impeller. That's your main element within the pump. It does all the hard work, and it's basically the rotational element in the pump. We need this impeller to be durable. It needs to be all the time. It needs to be there all the time to maintain consistent feed into the cyclone. So it's a very important element within the pump and then thus within the mill circuit as well. So this material, the impeller has to have typically a hard wearing material. It's got to be a hard wearing material construction. The best so far is the 27% chrome that is commonly referred to in the mining industry, which can handle abrasive material, but at the same time is also easily to produce. So that is one of the main drivers behind the impeller being of high chrome. The pump may be fully metal lined or rubber lined with a metal impeller. Now, the important thing to note here is we still, even if you change to a rubber lining, you'll still maintain the metal impeller. And reason for that is the impeller bears the brunt of all the abrasive and the coarse material that enters it from the mill. So it tends to be, we generally standardize on a metal impeller for mill discharge applications. Right, now just to take this further, I'm going to briefly focus on the basics of slurry pumping. Not just, it obviously applies to the mill circuit, but this is a typical curve that you'll see for any pump, any centrifugal slurry pump. You'll notice everything is based on water because it's not practical to have a curve developed for every abrasive or slurry that you can think of. Everything is different. Your dry densities are different. Your percentage concentration by weights vary all the time. Your particle size distribution also varies all the time. So it's difficult to make a curve up for every different variation. So everything is referred back to a water curve, and then what we do is we apply corrective factors. Now, just to elaborate on the curves, we have the head on the vertical scale, and typically the flow rate on the horizontal scale, and this is basically what determines how you select the pump. The size of the pump will be determined by the flow rate of the pump. Then the other important factors we have on this pump curve are the efficiencies and the RPMs, the speeds of the pump is going to operate at. Normally, you'll find maybe with water pumps you'll have a single speed and you trim the impeller, but here it's very different because it's difficult to make different trims of impeller with the material being hard, and therefore we vary the speed rather than the diameter of the impeller. And one other very important factor generally in slurry pumping is your NPSH. Okay, now we're going to just look at all these. We're going to see what happens with how you operate or where you operate on that curve, and see the effects that you'll have on wear on the impeller. So there's our curve again. Right, operating to the left of the curve of the BEP. Normally you'll see the BEP over there, that's your best efficiency line. If you operate to the left, these are the effects you're going to have. We normally refer to this as under BEP because you're well under in terms of flow. You're pumping less than desirable for that particular pump size. What's happening here is because you're pumping much less than the pump is designed to pump, we refer to as a throttling effect, because effectively the pump doesn't have enough to pump away. So you might be throttling by means of a valve or other effect, but it's a similar thing where you're under pumping. What's going to happen here is you're going to have recirculation within the pump because you don't have effective slurry to carry away. And then as a result of that, you're going to have excessive wear on your impeller and your liners because of the recirculation. Right, now we're going to look at the optimum position you should be operating on the curves. It's close to best efficiency. Generally, the tendency is to work to the left of best efficiency. People, I think, allow for a bit of expansion or increased flow rate, and that is the reason for doing this. You'll find here, like I said, you left up here best efficiency. This is where you tend to get your best efficiency out for your pump to operate where it's supposed to. The NPSH required, which we just touched on earlier, is low. It's within limits. It's normally where your design of your plant will have something within limits of what the pump requires. And as a result of that, you'll be operating basically in an optimal condition. You're going to have low maintenance and hardly any worries. Right. On the other hand, let's look at the over BEP situation on the right-hand side. As you can see, the curve sort of drop off, so it's considered to be the low pressure end of the curve. And one very important feature is as you progress towards the right of the curve, you'll see your NPSH starts increasing. Now that's one thing to be very sort of cautious about, because your NPSH available on site may not be adequate in terms of what the pump requires, and then you're going to end up typically with problems of cavitation. And as a result, you'll have the symptoms, which are typically vibration and noise. So let's just look at now what actual wear. Remember, we want our pump to be consistent. It needs to be there. The availability of the pump needs to be there. It needs to be pumping all the time. So we need to minimize the wear on the pump. Let's just see what the effects are of having an under BEP situation, an over BEP situation, and then an optimal BEP situation. Firstly, the under BEP, you'll notice wear will happen at the eye or the inlet of the pump or of the impeller, more on the leading edge. And you'll find once that starts wearing unevenly, it's on the one side of the vane. What will happen on the volute is the slurry will tend to recirculate, as we mentioned, and you're going to have cut water affected there adversely, and you're probably going to find your parts failing before or well ahead of their time. Similarly, with over BEP situation, where you're going to have wear on your trailing edge of the impeller and more to the outside, but this is also an uneven pattern of wear, and it could result in your impeller failing prematurely. Similarly with your volute liner, you're going to find instead of the cutwater side, now your pump is trying to overpump, and that's where you're going to encounter wear, and it's going to shorten the life of your volute liner. Coming to where we should be with our wear is, you'll notice this is operating close to BEP or preferably on BEP. And the thing here is, you'll notice that the flow and the vanes match. They match very closely. So what will happen here is you'll get very even wear. Right? Remember, your impeller is going to wear sometime or later. But the important thing is you are aligning your wear with the vane and the shape of the impeller, and therefore it will wear much more evenly and provide a better wear life, a longer wear life. Similarly, with your volute liner, you're going to find your slurry is directed where it should go. It's not impinging to any one of the sides, and therefore your volute liner and your liners in general will also have a prolonged wear life. Right, one other element we touched on earlier was the adjustment of the impeller and liners. I've marked a little red line. If you can see, this is your pump, and that is the clearance that you want to maintain to a minimum, because you want your impeller and your line is to be closed. You don't want slurry ingressing into that area because that will just speed up your wear, and also make your impeller more inefficient, and also give rise to more recirculation within the pump. So you want to avoid the situation. Conventionally, the adjustment of this impeller close to the liners has been via the bearing assembly. So this whole assembly where your impeller is attached to your shaft at the end, the whole assembly is adjusted, and thereby your impeller is then kept close to your liners. But the problem with this is you need to unscrew or loosen the bearing assembly from the cradle in order to achieve this, and also this can only be done when the pump is stationary or not operational. Recent trends in industry have made another allowance for adjustment on your liners, on the liner side as opposed to the impeller side. So what happens is there are pusher and puller bolts on this side, and these will actually allow you to adjust your lining close to the impeller. So you still maintain the clearance, and you therefore give the whole pump a longer life. Your liners will also weigh evenly in doing that. The one big advantage of this scenario is that you can actually carry this out with the pump still in operation. So, but it needs very trained hands, it needs skilled hands, but you've got to know what you're doing, and it's definitely a plus for having a multi-circuit pump in particular. The one other thing we've got to point out here is this arrangement can be a bit costly if you look at the smaller pumps, and therefore it's more practical maybe if you implement it on the larger pump units. But by the same token, on your smaller pump units, the facility of adjusting it via the bearing assembly might still be the number one choice, because the smaller pump has probably a smaller operation, so there's not so much downtime there. Just following up on maximizing the availability of your mill circuit pump. What you've got to do is one first option, or the first prize as I call it, is the standby pump, which is installed and part of the mill circuit. So essentially this pump will be a standby pump standing side by side with your operating pump. They'll be connected to the piping and everything. The only difference will be that the standby pump will be isolated by a valve or something, so at least it's not running, it's just there on standby, but nevertheless it's ready to go. So should your operational pump be needing overhauling, that pump stopped, isolated with a valve, and you switch over to your standby pump. So there's hardly any downtime if you implement this method. Then the other option we have is having a standby. It could be in your stores or something. So what could happen is you have the whole pump unit as a spare unit in your stores, and you can pull that pump in and remove the pump that's operational, take it out for overhaul, and then install the spare pump, so you continue your mill circuit operation. Right, this is obviously going to be the less costly option, because you're not installing different piping and valves, etc. So we're going down in terms of capital cost. The important thing about having your standby pump, which is just sitting outside or in your stores, is to have a very uncomplicated installation or reassembly. You don't want to have too many holding down bolts, for example. You don't want to have too much trouble taking out the existing pump to replace the new pump with, or the replacement pump with. So you've got to take all that into consideration. Then yet another option would be, and this obviously is now even less capital expenditure, is having pump sub-assemblies. You could have the wet end here stored as a separate assembly, your bearing and whatever, and replace them as and when needed. But obviously the big the downside of this will be the outside time that you're going to have, the downtime you're going to have. So you had spending less in terms of capital, but you're really incurring some costs when it comes to having downtime in your operation. And remember, you need to still maintain the tonnage per hour or tonnage per annum. One other important factor is the bearing assembly. I've mentioned it here, though this should be the least of your worries, because that should virtually last you for as long as the pump goes on, provided you've given it correct maintenance and adequate maintenance. And which brings us to managing and maintenance of the mill circuit pump. As we've been discussing, the typical demand is always your tonnage per hour, but what some people try and do sometimes is push the pump to its limit. So what they'll do is sometimes they won't even consider that the pump does have some limits, and they'll think increasing throughput, yes, let's speed up the pump. But now we've got to be very careful here, because pumps are designed and they are selected and sized to predefined parameters. So you give flow rates, densities, etc. at the outset of the selection of the pump, and that's what the pump supplier sizes the pump to do, right? And so remember, it's got the sizing of the driver, it's got a particular kilowatt motor selected to do that job. Now you can't just go willy-nilly try and speed up the pump, and then suddenly you find it's not only your motor that's going to be affected, because you'll be drawing far more amps than you were expecting to, but also you're going to promote, or you're going to speed up the wear in the pump. So you're going to have the effects of wear, and you're going to have quicker efficiency drop within your impeller. You're going to have your tonnage is going to start dropping off, and it's not just a simple effect of speeding up the pump. So it's going to affect, once your pump stops delivering effectively in terms of pressure or flow to your cyclone, your whole mill circuit is disrupted and affected. So the key here is to promote regular maintenance. You've got to keep your bearing assemblies properly greased or lubricated. It's also important to note that over-greasing is just as bad as under-greasing. So things have to be done. There are the manual lays out the intervals, the greasing intervals, etc. So that needs to be taken care of. The other thing that needs to be managed is the actual monitoring of the output of the pump. So that also needs to be kept a check on. You'll need to check whether your slurry being delivered is enough, whether you're on your cyclones, your pressure gauge will tell you whether you're getting enough pressure. So your output of the pump can be monitored, your amps that the pump is drawing can be monitored, and all those conditions actually can tell you whether the pump is still performing adequately. There might be wear within the pump, there might be a drop in the efficiency because of the impeller being worn or the liners being worn. So all those different parameters need to be kept in check, and then that is how you promote maximum availability of your pump. One other very important aspect of maintenance is observation. Now, this is what we've just mentioned, and monitoring your different parameters, your amps, the pump is drawing, if there's any noises coming out of the pump, the pump itself physically, temperature on the bearings, etc. And the important thing will be also to see once your output starts declining, so you can monitor this on your cyclones typically, see what output you're getting, your flow rate, etc. If that starts tapering off, the pump is about to wear. But now the important thing is, remember, we've discussed the adjustment of the impeller. You can still get this, you can get maximum life out of your lining of the pump. And we want to promote that as far as possible. So simple effects that you need to take care of is things like adjustment, little things that can be taken care of still to promote promote life with the existing components of the pump. Yes, there will come a time when the wear rate, etc., has exceeded its bounds, and then you need to obviously overhaul the parts that need replacement, etc. But now the important thing, this is why I'm bringing up the thing about observation, is you need to monitor what sort of pattern the pump wear develops. So if it's a couple of months as opposed to maybe your mill, you need to fit so many overhauls of the pump within a big shutdown for maybe a mill change out. So, this can only come through with monitoring and observation. Any new plant is different, every ore is different, the hardnesses are different, the wear rates would be different, and that can only come through with monitoring and observation. So what basically would happen here is you maintain your pump. Sometimes what might happen is you might operate your pump to the maximum, or there might still be significant wear life left on your pumps. And what might happen is, because there's a schedule shut, you might have to sacrifice whatever life your impeller has or your components have within the pump in favor of a scheduled shutdown rather than have a separate overhaul shutdown specifically for your pump. Because remember, like I said, it's one of the elements, one of the components in the bigger mill circuit, and you need to look after your mill and cyclones as well. Thank you very much.